Section 3.4, we're going to take another look at graphs and behavior. So in 3.3, we looked at the behavior in terms of it being increasing or decreasing. In 3.4, we're going to look at behavior in terms of concavity. So concavity as the idea of how the graph opens or how the derivatives are changing. So concavity definition, for a function f that is differentiable in the interval I, the graph of f is concave up if the derivative is increasing and concave down if the derivative is decreasing. And that's all well and good, but that's not really how we typically test the concavity. We test the concavity with the test for concavity. And what we actually look for instead is what happens to the second derivative. So if the second derivative exists and is positive, then the graph is concave up. And if the second derivative exists and is negative, then the graph is concave down. Okay? Now, this comes from this concavity definition. Graphs that are increasing happen when their derivative is positive. So the derivative of f prime is f double prime. And the derivative of f prime here is f double prime. So an increasing graph has a derivative that's positive, and a decreasing graph has a derivative that's negative. So we're taking this definition of concavity and we're applying what we did in the previous section where f prime is our function and we're looking at its derivative. That's where this test for concavity is coming from, okay? It will feel like we're doing the same steps, just one additional piece as we test for concavity. So directions say to determine the intervals where the graph is concave up and concave down. And again, we're starting with a fairly easy to do derivative, right? This is a polynomial. You may not necessarily know exactly what it looks like, but it is an x to the fourth, which means that on the edges of it, if you remember this from algebra or not, but on the edges of it, it's going to look like a parabola. And because the x to the fourth is positive, it's going to be opening up on the ends. So it might actually look like that, or it might look like some kind of a W. Those are the two possibilities here, okay? But on the edges of it, it's going to be opening up because the x to the fourth is positive. If the x to the fourth were negative, we would be opening downward on the edges. So this is the general idea. And so it's either going to have concave up everywhere, like this, or we're going to have some pieces where it's concave up and some pieces where it's concave down. Does that make sense? Okay. So let's actually do the calculus for this. We're going to take two derivatives. So what is the first derivative of x to the fourth minus 6x squared plus 2x plus 3?
4x to the third minus 12x plus 2.
Fabulous. Everybody good with that? And then we're going to do it again. So this one's not bad to take a second derivative of. Some of them are not so friendly. What's the derivative of the derivative?
12x squared minus 12.
Wonderful. 12x squared minus 12. Okay? After we take that second derivative, it's going to look just like the things we were doing before. We're going to set it equal to 0. We're going to create a number line. We're going to look for positives and negatives. But then we're going to identify areas where its concavity changes and so forth, instead of where it's increasing and decreasing and how that changes. So where does this equal 0? Well, this is 12x squared equals 12. So x squared is equal to 1. What's x? Yeah, plus or minus 1. We do get two values. It's really easy to forget that minus part, so be careful when we're looking at solving things that have square roots involved, right? So we are going to have a number line that has intervals beginning and ending with the negative ones and positive ones. I should make that a little bit bigger. Okay, again, we're testing points because whatever happens in this graph, it's going to be the same thing on the entire interval from negative infinity to negative 1. So it doesn't matter if we pick all the same value or not. but we need to pick a value in there to test. So tell me when you'd like to test. 0 will be in between. We will use that. What do we want to do before -1? -2. And maybe after 1? 2. Okay. Braden, you're not adventurous at all. Right there with you, buddy. That's what I do. Okay? Easy values. Pick what you'd like, though. And we want to test these values, -2, 0, and 2, into the second derivative. So all of this goes back up to the second derivative that we tested in. If you've picked nice enough values, you might be able to just eyeball it and know what happens. If it's a complicated function or if you can't see it, you're welcome to put 12x squared minus 12 into the y1 and then just let your calculator do it. All right, so let's do it together. If I put in -2, -2 squared times 12 minus 12, is it positive or negative? It is positive. How about 0? Negative? And 2? Positive. Okay. These positives and negatives do not tell me increasing, decreasing, because I did this from a second derivative. They tell me concavity. So, in some sort of sense, the positive means that it's like this, right? It holds water. And the negative is like this. It sort of dumps out the water. And the positive is, again, holding water. So, my concavity is that it's concave up from -infinity to -1, and then again from 1 to infinity. And it's concave down from -1 to 1. You might be thinking, well, is there something special about these places where it changes concavity? The answer is yes, there is. Those places where it changes concavity are called inflection points. So an inflection point for a graph f that's continuous is a location where the graph changes concavity from concave down to concave up, or vice versa. When that happens, this point is called an inflection point. So we had 2 of them on the previous graph, right? I forgot for us to check that. We should probably do that real quick. Let's go back and look at the graph on our calculator from number 1. Original equation, so x to the 4th minus 6x squared plus 2x plus 3. And I'm just going to put my window back to the Zoom 6 window, the standard window. And we see that W-ish shape, right? Remember, my graph was, or my sketches were not intended to be perfect. They were intended to show how things were adjusted or changing. And they do, in fact, look like what we were expecting. We have a concave up at the beginning, right here. In here, it's concave down, and then over here, it's concave up. So it matches our expectations. We could trace along, or we could eyeball it to see that and for sure that this is -1, and that this is actually changing over here at a +1. So it's harder to see on this one. -1, sorry, I pointed to the wrong place. -1 is right here, where it changes concavity, and +1 would be right here, where it's changing concavity. So it sort of splits the difference between the peak and the valley, and that's the place where it changes concavity. Okay, so point of inflection, theorem 3.8. If you have a point of inflection, then it will only happen when the second derivative does not exist, or the second derivative is 0. Oh, I'm sorry. Wrong screen. There we go. Thank you. So a second derivative equaling 0 is kind of like a critical point. It doesn't have a specific name like critical point did, right? But if you have an inflection point, it has this feature. The second derivative would have been 0, or the second derivative would be does not exist. Okay, we're going to do just a little bit into the next problem, but we won't finish it. Okay? So the directions ask us to find the points of inflection and discuss concavity. So it's kind of like what we did on the first problem, but it's got this extra piece that just says we're going to talk about the inflection points as well. This function, written out like it is, can be done in one of two ways. You can either multiply it all out from the beginning, which is totally fine and might be the easier option, or you can use a product rule and the chain rule in the middle of it because there's a chain in x minus 4 cubed. Okay? So I'm going to let you guys decide. Do you want to multiply it all out? Eventually we're going to have to multiply something regardless. So do you want to multiply it all out, or do you want to use chain rules and product rules? Somebody be able to make a decision for us. Multiply it out. Thank you, Sophia. Okay, so we're going to multiply it out. So if we multiply it out, we're going to leave the x alone. We have x minus 4 times x minus 4 times x minus 4. We take two of them at a time and we FOIL. So the pieces at the beginning I'm going to leave alone, or if you want to multiply them out together too, you could do that. I guess we could probably do that at the same time. So this is x squared plus 4x. That'd be fine. And then over here I would have x squared. The inside term's negative 4x, the outside term's negative 4x.
Minus 4x?
Yeah, thank you. I'm trying to go fast to get you out of here. So sorry. Let me slow down just a bit. Minus 8x and plus 16. Okay, did I get all the other pieces okay? Wonderful. All right, we're going to distribute the x squared through everything. So we have x to the 4th minus 8x cubed plus 16x squared. And then on the other one, we'll distribute the negative 4x to everything. That's going to give me a negative 4x cubed, positive 32x squared, and negative 64x. Did all that work out okay? No, I'm a little gun shy. We're good. Okay. There's pieces that can be combined, of course. X to the 4th is standalone, but I have a negative 8x cubed and I have a negative 4x cubed. That's negative 12x cubed. And then I have a 16x squared and a 32x squared. So how many is that? Positive 48x squared. And then I have my minus 64x. Okay. All right. Our derivatives will now be very easy, right? Okay, you pay for it somewhere. You pay for it either in the algebra at the beginning or in the algebra in the middle. We paid for it already today. So when we pick up on Monday, we'll be able to take the derivative and the second derivative quite quickly. All right, so we'll stop right there.